Hi everyone, this is the last mini lecture in the graph theory unit, and we're going to be talking about trees. A tree is a special sort of graph that can be used to model situations when there's only one root or connection between the people, places, or things that are represented by the vertices. So some properties of trees. First, the definition: a tree is a graph that is connected and has no circuits. In any tree, there's one and only one path joining any two vertices. Every edge is a bridge. Remember, what's a bridge? A bridge is an edge such that if you remove that edge from a graph, the graph will no longer be connected. So every single edge is a bridge, and a tree with n vertices will have to have n minus 1 edges. So let's look at a few graphs and determine if they are trees or not. Do they meet this definition? So first we'll ask, is it connected? Yes. Does it have any circuits? No. Is every edge a bridge? Imagine taking out any of these edges. The graph would no longer be connected. So yes, every edge is a bridge. And then how many vertices does this have? 1, 2, 3, 4, 5, 6, 7, 8. N equals 8. So we should have 7 edges. 1, 2, 3, 4, 5, 6, 7. And we do. So yes, this first one on the left is a tree. If you like, pause your video and determine on your own if B and C are trees or not. In the second one, it is connected, but it has circuits. So circuits are paths that can begin and end at the same vertex. So I could start here and make my way back along some path. So this one has 2 circuits in it. And it is not the case that every edge is a bridge. For instance, I could get rid of this edge and the graph would still be connected. So this is not a tree. And then lastly, this half of the graph on its own is a tree. This is a tree, but it's not connected. So if the graph is not connected, it automatically is not a tree. That's the first thing in our definition. So not connected, not a tree. So why do we need trees? What are these used for? Sometimes we're interested in increasing the efficiency of a network that we have, and that might involve eliminating redundant connections in a graph. So we're going to be looking for trees inside of graphs, and a tree that removes all the redundancy of a network is called a spanning tree. So a spanning tree is a subgraph of a graph, like a subset of a set, so it contains a subset of the edges, but all the vertices of a connected graph, and it has no circuits in it. So subgraph is an extra word in here that we don't have a definition for, but a subgraph is a part of the original graph that we started with, just like subset is part of a set. But we need to keep all the vertices if it's going to be a spanning tree. So consider this graph below. We want to find a spanning tree. So it cannot have a circuit. It needs to contain every vertex. There are 1, 2, 3, 4, 5, 6 vertices. So a tree would have 5 edges connecting these 6 vertices. And there's lots of different answers for how to find a spanning tree here. So maybe pause the video, take a second and find one on your own. And I'm going to draw in a few in different colors. So one example, I could start in the middle and go out. So just like a star. It's connected. It has n-1 edges. Every edge is a bridge, and it has no circuits. So that's a spanning tree. Other things that we could do, we could go, I'll do it in a different color, along this edge, 1, 2, 3, 4. Now I can't go back this way because that would be a circuit, but I could go down this edge to take a spanning tree. So I had 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. That's another example of a spanning tree for the same graph. All of the vertices are included, and a subset of the edges are included to make it a tree. So as you see, there are many possible spanning trees. You may have come up with a different one. There's several other ones that you could find. Sometimes if we have a weighted graph, we're looking for a minimum spanning tree. So remember, a weighted graph is one that has numbers or weights associated with each of the edges. And so when we have different weights, there may be a spanning tree that is better for our purposes. Typically, if we're talking about cost associated with edges, if we're trying to travel along edges, we want to minimize the cost. So a minimum spanning tree for a weighted graph is a spanning tree with the smallest possible total weight. So we're going to use this algorithm below for finding minimum spanning trees in graphs. This is called Kruskal's algorithm. So we can start anywhere. So first we're going to find the edge of the graph with the smallest weight and color it in or denote it some way. Then we're going to find the next smallest edge and color it in. And we're going to keep doing that, being sure not to create a circuit until all the vertices are included. And then the colored edges are going to make up our spanning tree. So looking at the graph below, we're going to start just with the smallest possible edge, or the edge with the smallest weight, and that is 75. So we'll color that in. Now we have our vertices D and C taken care of. Let's see, where's the next smallest that doesn't create a circuit? Well, we can't create a circuit yet with just two edges. The next one is 85. So now I've got 3 of my 5 vertices taken care of. Where's the next smallest weight? 90. And we need to make sure that this is not going to create a circuit. And it's not. For example, if this 120 had happened to have been smaller than 90, we wouldn't be able to take that edge because that would make a triangle here, which would be a circuit. We would have a closed-in connection there, which we don't want in a tree. But we don't have to worry about that because the smallest is 90. We can go out like that to B. Now we have to ask how to include A Or we can think about just finding the next smallest edge, as the algorithm tells us to do. The next smallest is, 95. That's good. I thought we were going to have to pick between these 120s, but 95 is just the smallest. So if we kind of extract just the tree, this is what our minimum spanning tree looks like. So maybe we're trying to get all the offices in a building on a network or something, and these weights might represent how much it's going to cost to wire from office B to office C, or how much like the actual length of wire that you're going to need between the offices. The minimum spanning tree would tell us how to get everybody connected in the smallest or cheapest possible way.